in keeping with the indeterminate form we have so far, we've got 0 over 0. We've got infinity over infinity. And we've got 0 times infinity, or infinity times 0. It doesn't matter how you write that. So we've got these three forms. And we also have these three forms. And these, since the exponents are 0 or infinity, we can do some logarithmic manipulation to show that they can be rewritten as 0 over 0. And in addition, we can do that with the last one, which is infinity minus infinity. And so when we look at, if we look at these three indeterminate forms, there we go. If we look at those three, then we can, let's do natural log of 1 to the infinity, then we can bring the infinity down in front, and we have infinity times the natural log of 1. And we know infinity can be written as 1 over 0. We know the natural log of 1 is 0. So we're looking at, we can write that as 0 over 1. We're looking at 0 over 0. So we can easily manipulate these by using logarithmic properties. And of course, these other two can be manipulated in exactly the same way. We can take the natural log of 0 to the 0 and get 0 times natural log of 0. That's undefined in itself. So, so we can just stop there because we come up with an undefined quantity. And then we can do the same thing here. We can take the natural log of infinity to the 0. We can bring down the 0 in front. The natural log of infinity is infinity, so we get 0 times infinity, which is 0 times 1 over 0, and then we can do them, multiplying the fractions to get 0 over 0 here. So we can easily show that all of these can come back to those 0 over 0 relationships. This one basically is 0 times infinity because that's, when we have natural log of 0, we don't have a defined, we have that asymptotic behavior at the y-axis. So, and then we can get the 0 over 0 as well. So, we get those things that we can easily re-express by just manipulating them using algebra 2 skills. For the case of infinity minus infinity, we can take a look at this as two expressions that that are really rational expressions, each of their own. So if we take a look at these rational expressions, we could really call this infinity over infinity minus infinity over infinity. And if we try to add those fractions, it gets a little kind of, abstract here, but we could call the common denominator infinity. And then the next thing we have to grapple with is, well, what is infinity minus infinity? And it's kind of circular reasoning in the sense that that's kind of the question we were starting out with. What is infinity minus infinity? Well, some people might look at that and say, hey, it's 0. And it's not really the case because infinity isn't a specific value. Some people might look at that and say, well, it's infinity. And so we could kind of look at both of those arguments. So for those people who want to say that it's 0, we'll look at that. For those people who want to say that no, it's infinity, we'll look at it in that respect. And so we kind of have these two parallel proofs, and we've proven that these are already indeterminate forms in of themselves. Because those are the two indeterminate forms that we started with. In either argument, we have the case where we come up with two indeterminate forms, as we combine that fraction, since really the whole premise of L'Hopital's rule is to evaluate rational expressions. We can just say that we come back to these two indeterminate forms. So in looking at this expression here, we have to kind of acknowledge that this is in fact a rational expression. When we take a look at that negative exponent on Euler's number, we can really write this as x to the fifth over e to the x over 100. And so, so we really have a rational expression. So we take a quick look at the limit here. We're approaching infinity. So we do have, if we plug that in, we can quickly confirm that we have an infinity over infinity scenario. So we can go ahead and take the derivative then of the top and the bottom. And this is kind of to point out that even if we take the value of this over 100, which is, you know, hundreds, we think of 100 as kind of a big number. When we're talking about it relative to infinity, this still goes to infinity, even if we have a denominator as big as 100. So when we're looking at taking the derivative here, the derivative of x to the fifth is 5x to the fourth. And the derivative of this is going to be e to the x over 100, and then times the derivative of this, which is 1 over 100. And it's still indeterminate. This is still infinity over infinity. So we're going to have to reduce it again. And so this is getting into the scenario of reducing it again. And so we're going to bring down the 4. We're going to take 5 times 4, which is 20, x cubed. And we're going to have to take the derivative of this again. So we have the 1 over 100 from the first time. And then we take the derivative of e to the x over 100. We get e to the x over 100 times 1 over 100 again. And this is still infinity over infinity. So we're still stuck in this indeterminate scenario. And if you can kind of see the pattern, looking at the top function and looking at the bottom function, this bottom function we'll never be able to get rid of that infinity term right here. But this we should be able to reduce down if we take the derivative enough times. So we'll kind of just keep taking the derivative here. So taking the derivative here, we get 20 times 3, which is 60, x squared. And taking the derivative on the bottom, we've got those two things, and then we take a derivative of e to the x over 100 again, and we get another 1 over 100. Still indeterminate, still infinity over infinity. So we're going to do this again. And then we're going to take the derivative of that. We get 120x. We get another 1 over 100 here. So we've got from the first derivative, from the second derivative, from the third derivative, and now let's take the derivative the fourth time. So the fourth time it's going to be e to the x over 100 times 1/100. So you might be seeing a pattern at this point, and we'll talk about that when we get done. Still infinity over infinity though, so we're going to have to take a derivative one more time so that we're really, what we're doing is we're engaging in a power reducing activity here, right? We keep reducing this power until it's gone. So we take the derivative enough times until it's gone. We have to take a derivative one more time here. So we have 1 over 100, 1 over 100, 1 over 100, 1 over 100. Those are all existing. Now we take that derivative one last time. So we get e to the x over 100 times 1 over 100 again. And so we get something that looks like this. Now we finally have 120 over this. And now we no longer have an indeterminate form. So when we look at this, we have 120 in the numerator. And as x goes to infinity here, it doesn't matter about all these things because this does go to infinity, even if we divide it by this enormous number. So we have 120 over infinity. It seems like a lot of work to get 0. but that's what we end up getting. So how can we get 0 quicker when we look at this function? So if we look at this function, we started out with x to the 5th over e to the x over 100. And we had to take the derivative how many times to get the power to reduce all the way down to 0 in the numerator. So we took a derivative 1, 2, 3, 4, 5 times. And that was to get rid of this power here. And in doing so, that created a coefficient that was 5 times 4 times 3 times 2 times 1. And we know 5 times 4 times 3 times 2 times 1 is 5 factorial. And so the top, we can then just look at the power and say, well, that's the factorial of that power. The bottom, we're going to have to take a derivative the same number of times. So we have, we know that every time we take the derivative of e to the x over 100, we get e to the x over 100 again. But then we get this, using the chain rule, we get this, the derivative of this, which is 1 over 100. So if you notice, we have 1 over 100 5 times. So we have 1 over 100 5 times. And so it's not uncommon then on multiple choice questions to see a multiple choice question that looks like this. What is the limit as x goes to infinity of x over 99 e to the x over 100? So we're going to look at this and we're going to say, well, that is the limit as x approaches infinity of 99 factorial over 1 over 100 to the 99th power, because we'll have to take the derivative 99 times to reduce that, e to the x over 100. And as long as that's going to take, it's still going to be 0. If we take a look at this example here, we have a fraction minus a fraction, and we have common denominators here. And of course, to really truly evaluate whether or not you have indeterminate forms, you really need a single ratio. So if we would write this as a single ratio, and we already have common denominators, it would look like the limit as x approaches 2 from the right of 1 minus the square root of x minus 1 all over x squared minus 4. And now we have a single ratio, and now we can kind of evaluate this and see if it is in fact indeterminate. So as we put in 2 here, we can see that we have a top that is 1 minus 1, so that's 0. And as we put a 2 in here, we have 0 on the bottom, so definitely indeterminate. So we definitely need L'Hopital's rule to evaluate this. So if we go ahead and evaluate this, then we're looking at taking the derivative of the top and the derivative of the bottom, and so I'm going to call the top g of x. So there's the top. So g prime of x is taking the derivative of this. So derivative of 1 is 0. Derivative of this is looking at, this is just minus x minus 1 to the 1/2. So it's 1/2 x minus 1 to the negative 1/2. And, this minus sign comes from the fact that there's a minus sign right out here. So we are looking at minus 1 over 2 times the square root of x minus 1. So there's g prime of x. I'll call the denominator h of x. And I'm just doing this because this one in particular is more complicated, so I wanted to do the steps for the derivative there. So taking the derivative of that, we get 2x. And so writing this back in its original problem, we have minus 1 over 2 times root x minus 1 over 2x. So we're looking at that, and it's tough to see if that's indeterminate or not, so I'm going to go ahead and simplify it a little bit by saying that's the same as this top numerator here, 2x minus 1 times 1 over 2x. And so we already can kind of see that it is no longer determinate since we have a numerator of 1. Whoops. And so it's the limit as x approaches 2 from the right of minus 1 over 2, nope, not 2, minus 1 over 4x times the square root of x minus 1. And so as x approaches 2, we can put 2 in directly and get a finite value for the denominator. So we have negative 1 in the numerator, and as we put 2 here, we get 4 times 2, which is 8, times the square root of 1, which is just 8, so the limit approaches 1/8. We again want to go ahead and kind of stick infinity in here and see if we have an indeterminate form. So 1 plus infinity is infinity. 1 over infinity is 0, so we have infinity to the 0. So again, definitely indeterminate. We need L'Hopital's for this. And this one gets a little tricky because we have an indeterminate with a power. And anytime we have an indeterminate with a power, we have to look at a logarithmic solution in order to evaluate the derivative. And the way we approach that is that we take the limit and we set it equal to y. And what that allows us to do is it allows us to manipulate this power up here by taking the log of both sides. So I'd like to work with natural logs, but you could do base 10 as well. But I'm just going to take the natural log of both sides. And so when I take the natural log of both sides, I'm going to take the natural log of y equals the natural log of this. The limit as x approaches infinity of 1 plus x to the 1 over x power. And this, taking the natural log of a limit is the same as taking the limit of a natural log. So we can really write this as taking the limit as x approaches infinity of the natural log of 1 plus x to the 1 over x power. And that makes it a little more straightforward as to how you deal with approaching the law of logs. So the law of logs says if you have a power, you can bring the power down to the front. And so that means we're taking the limit as x approaches infinity of 1 over x times the natural log of 1 plus x. And then we can go ahead and it's easier to see from a L'Hopital standpoint what we're taking derivatives of if we write this as a top-bottom fraction. So the numerator is 1 times the natural log of 1 plus x. So that is that, and then the denominator is x. So a quick check here, if we put in infinity, the natural log of infinity is infinity. And if we put infinity down here, we have infinity, infinity. Even rearranging it in terms of logs, we still have an indeterminate form. So we still definitely need to do L'Hopital's. Rearranging it algebraically is not enough. So we're going to go ahead and take the derivative of the natural log of 1 plus x. So taking the derivative of that is just 1 over 1 plus x times the derivative of what's on the inside here, and the derivative of what's on the inside here is just 1. And then the derivative on the bottom is x. So there's the derivative of the numerator and the derivative of the denominator. And I'm just moving all of that over so that I have space to write the limit as x approaches infinity of all of that. Okay, and then simplifying this double fraction here, we have 1 over 1 plus x times 1 over x. So you can see that it's no longer determinate, or indeterminate, excuse me, after we simplify it into a single top-bottom fraction. We get 1 over x times the quantity 1 plus x, or x plus x squared, however you want to write that. And so as x approaches infinity, 1 over infinity approaches 0. And what we have to remember is, in order to evaluate all of this, we go back to the beginning of the solution here, we ended up taking the natural log of both sides. So as the limit approaches 0, that is really the value of the natural log of y. And if we go back up to our first step here, this is our first step. We want to know what is the value for y, because that's the question. Y is the limit as this approaches infinity, as x approaches infinity of this expression. And so what if we set that equal to y, we really want to know the value for y. All we know right now is that the natural log of y equals 0. So what that is saying is that if we get this into exponential form, in other words, if we exponentiate both sides, we end up getting y equals e to the 0, and e to the 0 is 1. So the limit as x approaches infinity of 1 plus x to the 1 over x power ends up being 1.